Okay, so calculator active. Number one, people enter a line for an escalator at a rate modeled by the function given by R of t. So between 0 and 300 seconds, this is the rate at which people are entering the line to ride the escalator, to go on the escalator. But then after 300 seconds, there's no more people entering the escalator. So that's the scenario here. R of t is measured in people per second. The rate. And t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. So coming out, getting into line, there's a formula that changes over time, but then people leaving is at a constant 0.7 person per second. There are 20 people in line at time t equals 0. Okay, so before we even start, there's already 20 people in line before we start the timer. So part A, how many people enter the line for the escalator during the time from 0 to 300? Okay. So we want to know how many people enter the line. We don't have to count the number of people that's already in line, just the people who enter the line from 0 to 300. So we just rely on this integral here. Just take the definite integral then from 0 to 300, part A. We have people per second, so I want to take the integral antiderivative so I can make that unit rise from people per second into number of people. So R of t is in terms of people per second. You multiply that by time, and you can see that your time will cancel out, and you're left with people, number of people. All right, so okay, we can make the calculator do this work for us in your calculator. I like to enter it under y1 so that I don't have to keep typing in this function over and over again. So y1, I have that function entered in. Remember, you're always using variable x, never any other variable in your calculator. Okay, so once I have that, then math 9, definite integral from 0 to 300. $270. So just to convince you that the units is going to line up nicely, R of t is in terms of people per second. But then you're multiplying by dt, which is in terms of, which is a time unit. So if I do people per second times second, then the seconds cancel out and I'm left with people. So that makes sense algebraically as to why the units change. Okay, part B. During the time interval from 0 to 300 seconds, there are always people in line for the escalator. Okay, how many people are in line at 300? So we have to now include the people who are already in line plus the people who are entering into that line. So we like to, whenever we have these types of integral problems where there's a rate in and rate out, we like to have a formula that will keep track of all these moving parts, right? So the formula is total amount is equal to initial plus the amount added minus the amount removed. So that allows us to keep track of all these moving parts. For this problem, we can adapt it to number of people. So we can say the total number of people is found by identifying the initial number or the starting number plus the number of people added or number of people entered into line minus the number of people exited the line or exited the escalator. Okay, so let's let P of t represent the number of people that we're looking for. The initial number is P of 0. Number of people entered into the line will create a formula that will allow us to adapt to any time scenario. So we'll say from 0 to t of this r of x dx. Okay, I'm using x here so that when I plug this in, it'll turn into in terms of t, but just keeping that variable different. Now, the number of people exited is also a rate that we got to take the integral of, but the rate is a constant rate, so it's 0.7. It's not as complicated as this r of t. So it's just the integral of 0.7. We have a rate of 0.7 people per second. Okay, so I want to find the number of people in line 300 seconds in, so we can do P of 300. So P of 0 is 20. Make the calculator do this work for us. So we do math 9. Actually, we already have this, right? The integral from 0 to 300 of RT is 270. Subtract out the number of people who've exited. So it's going to make my function 0.7. 210 people exited. So I started with 20 people. 20 people entered in and 210 people left. So 300 seconds in, there's still going to be 80 people in line. Part C, after 300 seconds, there's no more people entering into the line to ride the escalator. What is the first time t that there are no people in line for the escalator? So we want to basically figure out after 300 seconds, there are no people entering in. How long will it take for 80 people to clear out and completely clear out of the escalator? So we know the exit rate is 0.7 people per second. I want to clear out 80 people. So I can do this, right? 80 people divided by 0.7 people per second, I'll be left with the time. Okay? Or you think of it this way, where this is my rate. My rate times time will give me the number of people that I want to clear out. So people per second times second will give me in terms of people. So if I divide both sides by 0.7, then time is just going to be the number of people divided by the rates. So 80 divided by 0.7. So this is going to be 114 seconds after 300. So we got to make sure that we add on this 114. It's going to take 114 seconds to clear out 80 people, but that's after all this time has passed. So the actual time from 0 is going to be 300 seconds plus 114. Okay, let's look at part D. Any questions so far? Part D says, between 0 and 300 seconds, at what time t is the number of people in line at a minimum? So that's a key word there. Anytime we're looking for max and min, which theorem are they trying to get us to use? Yeah, extreme value theorem, EVT. So EVT says, test the endpoints and test critical points. And critical points comes from the what? Setting the derivative equal to 0. So we already know that we're going to be testing 0 and 300. But we also want to be finding critical points. Well, we have our formula here. We have our P of t formula. So why don't we just find the derivative of this and set that derivative equal to 0? We can find those critical points, and we can test it all against this P of t function. So EVT, we're going to have to find our P prime. So let's think about the derivative here. Well, here's my P of t equation. P becomes P prime. That's fine. What does P of 0 become? Just 0, right? This is 20 people here. 20 will just go to 0. And then I also need to find the derivative of this integral here. Derivative of the integral, I'm just basically taking that away, and I'm just left with R of t. And then the derivative of the integral of 0.7, which is leaving me with 0.7. Okay, there's my derivative. Okay, so critical points is going to come from my derivative, set that equal to 0. And this is where we can use our calculator, right? Let's graph this function. And look for the x-intercept. Okay, so I have my function here. I have it stored under y1, but I didn't want to, in case I want to use it later, I'll leave that y1 alone. I just want to graph that y1 minus 0.7. So that r of t minus 0.7, I have it under y2, and I'm highlighting that function, and I'm unhighlighting everything else because I don't want to see all these graphs here. So I'm just going to graph that y1 minus 0.7 and see where that x-intercept is. Now, I may need to make some adjustments here because my bounds has to be between 0 and 300. So I'm going to adjust my window here to go from 0 and 300 because those are my possibilities as to where my x-intercepts could land. And then y min, y max, I like to just always start from -10 to 10. If it's too zoomed in or too zoomed out, we can always adjust those numbers later. Okay, so I see two x-intercepts. I mean, I have all this empty space here. Maybe I can go and adjust my y min, y max, maybe from -3 to 3 instead. Again, you can always make your adjustments, but you're really only playing with these 4 numbers whenever you adjust your window. That's all you need. Okay, let's find our 2 x-intercepts, and those will be our critical points. So do second trace, 0. Let's scroll to a point to the left of the x-intercept. Hit enter. Scroll to the other side of the x-intercept, hit enter. I get 33.013. We can put that down as one critical point. Same process. Critical point to the left, but near the other x-intercept, hit enter. Scroll to a point on the other side, hit enter again. 166. So we have our 2 critical points, 33 and 166, and we got to go through and test our endpoints as well as our critical points. So they all go into my P of T equation. To find the number of people at these moments in time. Well, we kind of already have P of 0 and P of 300, right? P of 0 is the number of people initially, which is 20 people. 300 seconds in, we found that to be 80 people. So we got to just do the test for 33 and for 166. Okay, so follow the formula here, 20 plus the integral from 0 to 166. Oh, sorry, 33.013. Let's do that first. My one function. Minus seven. 3.83 says round to the nearest whole number, so we'll round to 4. And repeat the process for 166 seconds, since that's the other critical point. $158, okay. We're asking for the absolute minimum, so it has to come from one of these 4 numbers, and the lowest number that we see is 4. So minimum number of people in line is 4 people at 33 seconds. Okay. Any questions with your calculator? Okay, you can also find critical points with your 36 Pro. You're just going to have to use your table of values and actually scroll and see when is the Y value going to change signs. And then you should be able to get it down to something close between 33 and 166. Initially, you may want to make your step a little bit larger, so you can kind of narrow down where your Y values are, where that x-intercept could be. But then you can continue to kind of refine and make the step a little closer if you know what numbers you're targeting. Okay, let's go to page 16, number 2. Okay, does anybody still need this page? The particle moves along the x-axis with a velocity given by v of t. Particle is at position x equals -5 at time t equals 0. Find the acceleration. So acceleration is just the derivative of velocity. We can make the calculator evaluate it for us using n-deriv feature. So I like to, again, hold everything under my y equation if possible. So I have under y3, I typed in 10 sine 0.4 x squared over x squared minus x plus 3. That's my velocity function. I want to work my way towards my acceleration. So I'll just do math 8, make the calculator find the acceleration at a moment in time. Negative 2.118. So that's my acceleration at time t equals 3. Okay, let me know if you have any trouble getting to those features on your calculator. Second, find the position of the particle at time t equals 3. Okay, so I have a starting point. I have velocity for displacement. So we always kind of go back to this formula, especially with particle motion problems. For any final position I'm looking for is always going to be initial plus displacement, right? Where do I start and how much progress do I make in that time interval? I want to find x of 3. So I want to start at x of 0. It's not that we're always starting at 0. It's just because we're starting at 0 because that's what's given to us. So if they give us a different starting point, then we use that starting point. And then we just bridge the gap between those two time intervals. So in this case, x of 3 equals x of 0 plus displacement. How much displacement distance do I cover in that 3-second interval? And make the calculator find that for us. Okay, math 9, depth integral from 0 to 3. So this is the progress that's made. I'm starting at -5, but then I'm able to move forward 3 units. I'm going to end up at negative 1.760. Part C, evaluate the depth integral from 0 to 3.5 of v of t. This is displacement. Evaluate the depth integral of the absolute value of v of t dt. This is total distance. So the difference here is that your displacement is just going to tell you how far you are from your starting point. But your distance is going to tell you how much you actually travel in that time interval. So if you're going back and forth in that time interval, then we count all those as positive distance. So typically, if you're only going in the same direction the entire time, these values should be the same. But if there's any backtracking, then this should take the larger value. Okay, your total distance should never be smaller than your displacement. At the very least, the distance will be the same value, if not greater. So in your calculator, you'll get 2.844 if you do the displacement. It's the object's displacement or the change in position in that time interval. But if you enter in using absolute value, okay, the way you get to that is you do math, number, ABS. That will take you to absolute value. Make sure though that your absolute value goes inside the integral notation but then outside the velocity function. Right? You don't want to put it all the way out here as absolute value. So let me show you what that looks like. Once you're inside the integral, you can call that absolute value function. So math number ABS. So you got the absolute value bar showing. Now you can insert the velocity function inside of that. It may take a minute to register, but eventually it will take you to 3.734, 3.737. Okay, part D. A second particle. So we have a first particle given by v of t, but then there's a second particle that moves along the x-axis as well, but it has a position function of t squared minus t. At what time t are the two particles moving with the same velocity? So ideally, if we can compare the velocity functions, we can figure out the time where they're moving at the same velocity. But we need to first get to the velocity function so we can kind of compare apples with apples here. So what's the velocity function for the second particle? Okay, just go through power rule, right? T squared minus t becomes what? 2t minus 1. Yeah. So if we have our velocity function for our first particle, and then we have a velocity function for our second particle, we can simply set them equal to each other and then solve for t. If we solve for t, we can figure out at what time are their velocities going to be the same. So we take our first velocity function, we take our second velocity function, we set them equal to each other. Now, if you take a look at this is not going to be something that you want to solve by hand, right? We'll make the calculator do the work for us. So I can subtract this 2t minus 1 over to the left side. And that way I can just let my calculator do the work for me. I'm going to graph this function and then follow the graph to the x-intercept. And that will tell me at what time will these be equal. So I put that under y4. I have it y3 minus parentheses 2x minus 1. And I'm just going to highlight my last graph because I only want to see that graph. Go to your window to adjust your window. You know that you're looking for a value between 0 and 3.5. So you can just adjust your x value to be between 0 and 3.5. Right, let's see if these values are enough. If it's too zoomed in, we can always adjust those numbers. Okay, so this is fine. We're able to find that x-intercept there. Okay, so at 1.57 seconds, the two velocities will be the same. The two particles will share the same velocity. Okay, so out of the FRQs that we've done, this is one of the easier ones. We don't know what's going to be like next Monday, but hopefully there'll be one or a few of them that'll be nice and easy like this. Okay, number 3. Page 17. Okay, graph of a continuous function, g, with the derivative of the function f. So they're telling us that g is same thing as f prime. This is the derivative graph for f. Function g is a piecewise linear, so you can see that all these made up of different functions, all formed by linear graphs. Until we get to 3, then it turns into a parabola, and that parabola is defined as 2 parentheses x minus 4 squared between 3 and 6. So part A says find, given f of 1 equals 3, what is the value of f of negative 5? So if we have a starting point, we're looking for f of negative 5, and also we have an f prime. So this goes back to this final position equals initial plus displacement. That really comes in handy for a lot of these problems here. Now, this is a good one to go over because I want to point out something that a lot of students make, or mistakes that students make here, even though the formula is very straightforward. But when things are going backwards, it's easy to skip a step. So let me show you what I mean by that. So here's the formula. My final position equals initial plus displacement. Okay. Okay, so this is where I see some students run into some trouble here. It's having to do with these values here. Okay. And the reason why this gives some students trouble is when we're working backwards. When you're working backwards, typically what's going to happen is you're just naturally going to want to go from left to right, which is fine, but not initially. Initially, you got to make sure that these numbers are matching. Okay, even if you're going backwards, you got to make these numbers match. Now, after you have everything set in place and you decide that you want to flip the bounds, you can then flip the bounds, but then you're actively making that adjustment, and then you're remembering to putting a negative here. So I want to find f of negative 5. But I'm starting at f of 1. Now, f of 1 is to the right of my endpoint. So we need to go from 1 to negative 5. But I think a lot of students will look at this and say, well, I want to go from left to right, so I want to go from negative 5 to 1. Now, if you jump to that conclusion, you're not making the adjustment, and so you're going to forget to change that sign to a negative. So always start with what the rule says, even if you're going backwards initially. But you want to make sure that these values are the same because I'm starting at 1 and I'm ending at negative 5. I want to establish that relationship first. Now, if you realize that I want to read the graph, I want to total the area, and I want my bounds to be in order, now I can flip the bounds and now I can change the sign. But you don't want to skip that step. If you skip that step, your sign's going to be off, and that's going to throw off your answer. Does that make sense? So I see a lot of students run into an issue here, not making those the same to begin with. And now we realize that if I want to read this graph, I want to read from left to right, I can now change the bounds. But as I'm doing that, I'm changing the sign as well. Now I can go to my graph. Okay, so we know f of 1 is 3. Come back to that. The integral from negative 5 to 1 is the area between the graph and the x-axis. So let me shade those in so you can see what we're dealing with. So I got a rectangle here. I got a triangle here. And I have a triangle here as well. Okay. Careful that we are just above and below the x-axis. Below is negative and above is positive. So the area here, 3 times 3 is 9. So let me call this negative 9 here. This area here, 1/2 base times height. That's below the x-axis, so I want to say that's negative 3/2. And this portion is above the x-axis. So 1/2 base times height, 1/2, 1 times 2. That's just going to be 1. I already made my adjustment on the front end. So whatever I see, I can just copy those signs down exactly as I see it. F of 1 is 3 minus parentheses. Let's add up all these numbers that we see in front of us. We got 2 regions below the x-axis, so that's why they were negative. We got a region above the x-axis, that's why it's positive. Now, this is non-calculator, okay? You can leave your answer like this and you're perfectly fine. Even though the answer cleaned up is 25/2, leave your answer in unsimplified form, you're fine, okay? I think the only time where unsimplified form is not quite enough is if you're dealing with trig. So if something has like cosine of pi/3, you got to make that go to 1/2. Okay, so they may take off points if you're not getting your trig function evaluated far enough. But if anything is just multiplied and added together on non-calculator section, you're not going to be taking points off if you don't simplify. In fact, you're encouraged to leave your answer unsimplified, because why continue working on the answer if you're already going to get full credit, right? If you continue to go to this step, you're introducing the possibility of making a mistake. If you have this and you make a mistake here, they got to take points off here because you made a calculation error. And also you're spending additional time that could be elsewhere, right? Especially since your time is going to be limited in terms of how much time you have on each problem. Okay, part B. Part B says evaluate the definite integral from 1 to 6. So integral from 1 to 6 is this region here. Now, if you look at the integral from 1 to 6, we have a portion that's identifiable geometric shapes, which we have formulas for that. But then suddenly from 3 to 6, now the area under the curve is under the parabola, and this is not a geometric shape. And because of that, we have to rely on definite integral of g of x to find that area for us. So for B, if I want to find the definite integral from 1 to 6, I want to kind of strategically split these up into regions that can be found geometrically versus a region that needs calculus to do. So I'll say integral from 1 to 6 can be split into the region from 1 to 3, which is just going to be a rectangle, plus the remaining region, which is the integral from 3 to 6, and that requires me to use calculus on this curve. So this piece we can use just by using width times height to get that rectangle, but this piece we got to either go through expansion or use substitution. So this is one of those cases where you could either expand or use substitution, but typically most problems you don't have both choices available, right? You always want to try to see if you can expand first. Expansion is not bad. You can expand this out, but you got to do power rule multiple times. Maybe it's a little bit cleaner to go through use substitution. What could be our U value there? Yeah, this is a nice, easy U value. There's no derivative with variables that's left over. This should end up with a power rule for us to apply. Okay, we make our substitutions. We're left with power rule here. So 2 times U cubed over 3. We bring that out as 2/3. And that gives us 2/3 U to the 4th over 4. Oh, sorry, I already did power rule here. My bad. I already did power rule, so my integral should be gone. Okay, sorry. 2/3 U cubed over 3. Du is also gone. I already did all the calculus here. Now I just want to bring my original variable back. And then work in my upper and lower bounds. Six minus 4 is 2. 2 cubed is 8. minus lower bound, 2/3, 3 minus 4 is -1. -1 cubed is -1. So 2/3, sorry, 16/3 plus 2/3 is 18/3, and 18/3 is equal to 6. So the area of this rectangle here, from 1 to 3 is width times height with an area of 4. So that's the first part. The second part, we use U substitution to get 6. And so our total is 10. Okay, let me just see if I can finish part C and D. These are pretty quick. Part C says, between -5 and 6, on what open interval is the graph of f both increasing and concave up? So remember, you're looking at the derivative graph here. So anything above the x-axis is positive slope. Anything below is negative slope. Increasing would have to be above the x-axis, and concave up would have to be positive slope. So I'm looking for portions of the graph that's above the x-axis and showing me positive slope. So it's going to be this portion from 0 to 1, and then from 4 to 6. Part D, find points of inflection. So if you're looking at the derivative graph, your points of inflection are going to be your peaks and valleys. This is too wide to be a peak, so we don't include that. The only peak or valley that we have is at 4. So increasing and concave up from 0 to 1 and 4 to 6. Point of inflection on the derivative graph is peak or valley of the graph. Hills or valleys of the graph, and there's only one valley, so it's only going to be at x equals 4 for t prime change in sign. Okay, so help session this afternoon, I will go through number 4 through 6. Your homework is the 2018 FRQs, which I'll send out a reminder this afternoon. It'll be pages 15 through 20. Okay, tomorrow we'll do 2017 FRQs, and then Friday we'll do 2016 FRQs. Nice to get 5 years worth of FRQs under our belt this final week before AP exams. Yeah. Yeah, R2 minus 0.7. You got to go all the way through. There we go. Have a great day, guys. See you tomorrow. Thank you. Have a good day. Thank you. Oh, Friday. Shoot, I gotta. Well, how about this? I'll just send it to you. Just remind me. I'll send it to you Friday morning. But I gotta proctor AP exam, so it's okay. You can be offline, and I'll give you a 3-hour window, and just send it to me by early afternoon. And you can start working on it around like well, what's your schedule like?
I don't know. I just texted him and he's like, I can do Friday. I can ask what time. Okay. And maybe I can get back to you tonight and let you know.
But either way, I do want to. I gotta send it to you before third period because I gotta be down at the gym. Okay. So I'll send it to you maybe around 10 or 9 o'clock to remind me. I can send that to you, and then whatever time you start, you do a 3-hour window to get this. Okay. All right. Thank you.
I might have missed something. I don't think I missed it, right?
You're trying to graph it, right? You're trying to find that x-intercept. Okay, these may be a little too big. Yeah, so if you don't see the graph, you may want to just start from -10 to 10 just to see where you're
Yeah,
at.
I did that and it was just like, oh,
Yeah, this feels a little better there.
okay, because before.
Oh, and then also we don't have to go all the way to start at 0.
Yeah. Okay, all right, thank you.
Can I get any like packets or anything I might miss?
Yeah, if you miss anything here, it's on that back page here. If you don't have it, I was here Friday. Yes, I think all this. You have time today? Oh, okay, okay. Okay, you have time tomorrow or you're off? Oh, okay, that's right.
Is this the FRQ packets now?
Yeah.
Like, can I show you 13 through 22 tomorrow?
Mhm. This 3 days.
Just take the multiple choice day one, so string launch and actually hearing this.
Okay. You stay at your desk, do it?
Yeah.
Okay. You can leave your.
It's also
things
on
here.
the
I can phone up here.
Thing is taking a beating. This is just this stuff. Yeah, because I had to order the rest of it, so that was. Case, best case, I got what's I can't really reach, but I'm getting back from Disney at 3 a.m. on Monday morning. That's so. Yeah, 5 hours later. What do you want Disney for? Tournament. Oh. Well, that's if we get to the final. So if we get to the final, I'll get home at 3 a.m. Monday morning. No. Yeah, it's a cool team. But I might not. Probably should stay awake.